Welcome back. This is video 4.11 on factor analysis and factor scores for simplest case data with a rank of 2. Now if you think about the videos that we did previous to this, we can do the same analysis on the same data matrix, well, a similar data matrix that is not actually full of rank, a matrix with a rank of 2, where we account for all of the variance in the 3-variable data set within a reduced 2-factor space. Now we talked about rank when we did some videos in chapter 3, and I believe that was video 3.23, but basically the rank of a matrix is defined as the number of linear independent rows or columns of the matrix. So the largest that a rank can be is the smallest of the number of rows or the number of columns. So when we're talking about rank of 2, I'll actually show you. Let's use the same data set that we had before, except we're going to change 2 numbers. Before we had in the third variable 16 and then 20. We're going to change this to 20 and 16. And then we'll go down with 9, 15, 20, and 10. Now, let me first get the average of these so we can get deviation scores. So notice that this 6x3 matrix here of data is almost the same one as we used before. We just switched the 20 and the 16, for which the only difference that we can see in the upper 2 values here in 20 and 16, it's the only difference that we can see. But you can notice that on every row, the value of the third variable is the sum of the values in the first 2 variables. So 8 plus 12 is 20, 6 and 10 is 16, 5 and 4 is 9. And that continues throughout. That is what makes this a matrix of rank 2 as opposed to rank 3. Because variable 3 is a linear combination of the other 2 variables. So let's get the deviations of this so that we can get the covariance matrix. So we have our raw data, and we're going to subtract our means to get our deviation scores. And then to get the centered sum of squares and cross products matrix, highlight our raw data, and multiply the transpose of that times the deviation scores. And now to get the covariance, we're going to take our CSSCP and divide by the degrees of freedom, which is 5. And that's what we get. Now if you look here, these values in bold, 5.2 and 7.2, are the ones that have changed from the previous data set, and that's because variable 3 has changed. Now when the covariance matrix is not full of rank, that is when there's a linear dependency, the third column of covariances is the sum of the other 2 columns. So we can see that 5.2 plus 17.2 is going to equal 22.4. Same with 1.2 and 16 and 4 and 1.2. Now the correlation matrix is also going to differ by the 2 values in the same locations as here, and I'll show you that down here. So we're going to have this equal 1 divided by the square root of 4, which is our variance up there in the covariance matrix. 1 divided by the square root of the next one, which is 16. And then 1 divided by the square root of 22.4 with zeros on the diagonals. And we're going to do matrix multiplication. We're going to have to do that twice. So take our E matrix times covariance matrix times the E matrix again. And I should do that across all of it. Okay, so notice that this third variable also changes from what we had in the previous example when 16 and 20 up here were changed. Now, as we factor this correlation matrix by the process that we did in the previous videos, we can get a factor analysis summary table, which what I've done here is just copied what we had in the book and put it in here. And notice that the three communalities are equal to 1, signifying that all of the variance is accounted for in each variable. That's really cool. Also, the two eigenvalues sum to 3, indicating, so we see here 2.132 plus 0.860 will equal 3, which is indicating that all the variance in the entire data set is accounted for by the two factors. Wouldn't that be great if this was a real data set and everything worked out like that? It would be awesome. The factor scores for this rank of 2 data are obtained from the following equation, which I'll show you on this worksheet. So this equation, y equals z, z times t, it's been used in a previous video, in that y is the factor scores, or the latent variable scores, and z is a manifest variable scores. T is just a transformation matrix. So when we multiply these together, we get those values. Now the factor scores in this case reproduce the information in the original data set completely, since the two factors in this case account for all the variance. Now when we go to this equation, z equals y times f transpose, y being what we just got, and f transpose being the factor scores that we got from the table here. Sorry, I didn't mean to do that. We just took the transpose of that and put it here. When we multiply those together, you can notice that we see that the process is completely reversible. So when we do this, we get z again, with obviously with some rounding error. And actually, I realized there was a mistake. This should be 1.5, and this should be negative 0.5. And the reason why it turns out this way is z is actually derived, as we talked about in the previous video. Z is derived from the matrix of deviation scores times the standardizing matrix E. So if we go back to our data here, we multiply this deviation score matrix times E matrix to get z, which is once again our manifest variables. So this should be 1.5 and this should be negative 0.5, and then now we see that it's completely reversible and we get the correct values. So there you go. That is a demonstration of factor analysis and factor scores for simplest case data with a rank of 2. Hope you have a good day.